So far, the only randomness we've considered is from quantum mechanical measurement. Consider, for example, the state of polarization of a photon. So far, we could write a general state of polarization as this kind of expression. Here, H would represent a horizontally polarized photon state, and V would represent a vertically polarized one. And we could write down a general state of polarization of a photon as some complex number, perhaps, times the horizontal polarization state, plus another complex number times the vertical polarization state. Suppose that we measure such a state like this. So we're going to have a source of photons with some controlled polarization. Specifically, they're going to produce this polarization state. And we can then use, for example, a polarizing beam splitter that separates horizontal and vertical polarizations. So here's such a device. It's relatively straightforward to make devices like this. You can make them from pieces of glass and other materials. And this will split out the horizontally polarized photons and the vertically polarized photons, or components. And it will put them on different detectors, if we like. So what we could call the vertical detector and what we could call the horizontal detector. Well, with an apparatus like this, we think we can perform quantum mechanical measurements. And for this state that we have here, we expect probabilities AH modulus squared of measuring horizontal polarization, so getting a photon measured on this detector, and AV modulus squared of measuring vertical polarization, so getting a photon detected on this detector. That's what we think would happen with our process of quantum mechanical measurement. And we can do this kind of experiment, and we do indeed get these kinds of results. Now, we must have, for our optical polarization, of course, that the sum of the squares, the modulus squares of these two factors here, is equal to 1. And hence we could also choose to write that AH is the cosine of some angle and AV is the sine of some angle multiplied by a unit complex factor. Here we're presuming that there may be some other overall complex unit factor that might multiply the whole state, but it doesn't matter for us in describing the polarization state of a photon. Delta equal to 0 here would correspond to linear polarization. Theta would then be the angle of the optical electric vector relative to the horizontal axis. When delta is not equal to 0, the field is in general elliptically polarized, which is the most general possible state of polarization. Delta equal to plus or minus pi over 2, with theta equal to 45 degrees, those together give right and left circular polarization, for example. Well, we can always build a polarizing filter, or what is sometimes called a compensator, to allow passage of a photon of any specific polarization. And it can do that 100% of the time, at least in a suitably perfect version of such a device. And that is true even if you start with elliptical polarization. So even if you have the most general possible polarization state of a photon, it is possible to build an optical component that we could call a compensator that allows 100% of those photons to pass, and ones that are in the orthogonal polarization state, for example, will not pass at all. We could arrange to delay only the horizontal polarization, for example, by a compensating amount minus delta, to make the photon linearly polarized, so turning it from elliptical to being linear. And then we could rotate the polarization, or indeed even the apparatus, by an angle theta so that the photon was always passed through. And for example, we could set that up so that the photon always went through, say, to the vertical detector. When we can make a polarization filter or compensator so that we can get 100% of the photons to one detector, So here's our polarization compensator we're putting in now, and the idea is that no matter what state we've chosen here, we can always design this in such a way that 100% of the photons would go through to here. We say that the photons then are in a pure state. Here, that state would be this one. So they started out in this state. We can build a compensator such that all of the photons end up going through to the vertical detector. If we can do that for a given state, then we can call that state a pure state. All the states we've been considering so far have in fact been pure states. A compensator could then be made to pass any particles in any one specific quantum mechanical state, with 100% efficiency to one detector. Suppose we have a beam that is a mixture from two different independent lasers, 1 and 2. So here's laser 1, here's laser 2, and we have what we call a non-polarizing beam splitter here. And what we imagine that does is it takes some portion of the photons from this laser, passes them through, some portion from this laser, reflects them through, without changing the polarization states of either of these beams. So this could be made from a partially reflecting surface, for example, partially reflecting mirror. Well, we presume that laser 1 then, in this beam here, now contributes a fraction, P1, of all the photons in this beam, and laser 2 contributes a fraction, P2. Then the probability a given photon is from laser 1 is P1, and similarly, there's a probability P2 that the photon is from laser 2. Presume also that these two lasers give what we can think of as uncorrelated photons of two possibly quite different polarization states. So psi1 from this laser and psi2 from that laser. And those will be the polarization states also of the photons from these respective lasers in this beam. That's the idea here. There is now no one setting of this compensator that will in general pass all the photons from both lasers through to the vertical detector. If we set it up so that it passes all of the photons from this laser, then because this polarization state is different, it will not pass all of those photons. And vice versa, if we set the polarization compensator to pass all the photons from this laser, in general, it will not pass all the photons from that one once we go through the polarizing beam splitter towards the vertical detector. Hence, we cannot simply write this state as some linear combination such as B1 psi1 plus B2 psi2 of the two different polarization states. If we were able to do that, we could construct a polarizing filter, the compensator and all of this here, to pass 100% of all of the photons. So the state of these photons is described differently as a mixed state, in contrast to a pure state like this one.